Yeah, okay, welcome everybody to the mathematical physics seminars. Our speakers today is Larisa Jonke from the RBI Institute of Zagreb, and she will tell us about Dft Algebraic and curved L-infinity algebras. Please, the stage is yours.
Thank you, Eugenia. Thank you all for coming. I'm very happy to give this talk in Prague, although it would be so much better if it was really in Prague. Okay, so I would like to tell you about some recent work I did with my PhD student, Clay Gruco, about Dft algebroids and L-infinity algebra. So just to sort of start with some setting, just 2 lines about general motivation, why are we looking at this problem. And it comes essentially for me from string theory, in a sense, motivated by nice generalization on standard stuff we love and know from field theory. In a sense, what we learn from string theory is that if we think of space-time probes being spatially extended like strings and brains, these spatially extended probes can wrap compactified spaces, and they are in this way they are sort of sourcing dualities, interesting dualities in string theory, for example, target T-duality. And also being extended, they couple to higher gauge potentials, thus leading us to higher gauge theories in this sense. And what we learn, and this is the topic of this talk, is that relevant mathematical tool or geometric tool in a way are these of algebroids and L-infinity algebra. So in a way, generalizing our ideas of symmetry, which we were discussed before, sort of in a field theory usually. And the question that motivates my research on these topics is how this generalized symmetry can be incorporated in a field theory. So in this talk, I want to exemplify some of these generalized symmetries in the context of double field theory, in particular using L-infinity algebra framework. And the short plan of this talk is that I would first introduce you to some basic data of double field theory. Then I will tell you how we define double field Dft algebroids and how these 2 things are related. I will show you how to write Dft algebroid in terms of L-infinity algebra, and then I will tell you why is this important and what are our next steps in this line of research. So to start with double field theory, it's a proposal for a field theory defined on double 2-dimensional configuration space with manifest T-duality. Some old initial references go back to 90s to Dft, Zeitlin, and Siegel, but in the incarnation we know it and work on it today goes to work of Chris Hall, Barton Zwieback, and Olaf Holm. As I said, it's field theory defined on 2D configurational space-time, so it uses a double set of coordinates. Do you see my pointer?
Yes.
Anybody? Okay, thank you.
Yes.
So we use double coordinates. Capital letter will always denote double set of coordinates, being it curved or flat, space-time or bundle. So we have double coordinates, the standard coordinates, which we extend by another set of double coordinates. In double field theory, in simplest setting, the field content of the theory is actually the common bosonic part, Nevers-Schwarz part of the string fields, here being only so metric, B field, and dilaton. And in general, they depend on the double coordinates of all coordinates. The theory has a global symmetry, ODD, group ODD, with ODD invariant metric. This is constant metric with the signature DD, where these A and B indices, as I said, are curved indices, and this metric raises and lowers these curved space-time indices. The nice part of this doubling procedure is that you can, in this setting, nicely pack your standard background fields, string background fields, metric, and a B field together in a ODD covariant object that is called generalized metric. This calligraphic H with double space-time indices A and B. This is one particular parameterization given here, just to see an example. It's not unique, obviously. Where this generalized metric lives in the coset of group G over H, which is actually here double Lorentz. You can, like in standard case, always pack. You don't have to use metric. You can use tetrads or field binds. So we have a d-dimensional bind and a B field, and you can package it nicely also if you want in generalized bind, which is element of this group, ODD group G. This bind satisfies this relation. So standard relation with the field bind contracted with ODD metric gives you actually another ODD metric, this time in the flat indices, and this is also constant, and it's used to lower and raise indices in a bundle, so on the flat indices. And obviously dilaton can be packed in the G ODD scalar, which is standard part, which is standard dilaton plus determinant, square root of determinant of metric. Once you have packaged your field content in ODD invariant way, you can write ODD invariant action in 2D dimensional space-time. You have the dilaton, and then there is some function which is very long and not very illuminating of this invariant generalized metric H and invariant dilaton D. Or if you want, you could write it using also this generalized bind and again dilaton. And this is known from 2010 and this nice review of exploring double field theory of the Argentinian group, which is I'm using often. And this action possesses also local gauge symmetry. So you can, there is a gauge symmetry also of the action, which is generated by ODD vector. So remember, these are double indices. So ODD vector, which generates this local gauge symmetry. And for example, this is action of this. This is the gauge transformation of general metric given here with this expression. This is defined, this is called generalized Lie derivative. However, your action is not automatically invariant under this local gauge symmetry, and maybe you know it, double field theory is constrained. In order for the action to be invariant under the local gauge symmetry, you have to impose you need to impose certain constraints. There are two distinct constraints in double field theory. The first one is this: when you have two double space-time derivative contracted with your space-time ODD invariant metric acting on a single field. It's called B constraint. Actually, it corresponds to level matching condition of string theory. However, it turns out that you have to actually constrain theory much stronger. You have to apply this sort of derivative operator on the product of any fields. So this is the constraint you have to impose on all your fields in a theory. Also, on all the fields in a theory. And only when this strong constraint is satisfied, the action is gauge invariant. What is important for us is that this algebra of gauge transformation of this algebra of generalized Lie derivative in double field theory closes. So the commutator of two gauge transformation again is a gauge transformation, closes only after imposing the strong constraint, and this bracket, so gauge transformation along the vector epsilon 1 with gauge transformation along the vector epsilon 2 will close again in the gauge transformation along the bracket, and this is called C bracket of these two vector fields of this form. However, what happens is that when solving the strong constraints, so you impose certain constraints on your fields, also on all the fields in the theory, including your vectors here, which generate the gauge transformation. In essence, it amounts to eliminative half of your coordinates you introduce to be double. So in a way, you are saying like your physical space is just half of degrees of freedom. Unfortunately, when you do this, double field theory reduces just to ordinary supergravity in different duality frames. And for us, also the C bracket of this gauge transformation reduces to the Courant bracket. So the question we posed is, can we define a consistent geometric structure based on a C bracket before reducing the theory by strong constraint? And there are sort of two answers existing. And the first answer was given by Andreas Desser and Christian Zeman in 2016, who said, yes, you can do it by starting construction from Vinogradov algebroid over double space-time, getting certain geometric data, which they recognize as being pre-NQ manifold. So non-negatively graded supermanifold with the vector field Q who doesn't square to 0. So it's a pre-Q manifold in a sense. And in our construction, we did actually the same starting point. It's just that, honestly, when we were writing the paper with Thanasis, Pekshen, and Richard, we just didn't think about Vinogradov. We just started with the coherent algebroid over double space-time, but this is the same thing. And we obtained the same set, basically, of geometrical data, which we interpret as double DFT algebroid. The starting point for both of these constructions is actually the same, and it's based just on the simple observation is that in double field theory, you are doubling your target space, your space-time. It becomes 2D space-time, while Courant or Vinogradov algebroid, basically these are generalized algebroid with generalized bundle over let's say d-dimensional manifold, but the bundle is sort of 2D dimensional. So you are in this algebraic construction, you are doubling the bundle, while in double field theory, you are doubling the base. So both Andreas and Christian, of course, and us, we just say, okay, let's construct this double bundle over a double space-time, and then we project to obtain sort of double field theory over double space, but sort of not double bundle. So as I say, the starting point and the geometrical data obtained are the same. The difference is only how we package or explain what are these geometric data we obtain from this construction. And for us, it was the easiest way to see it is through construction of L-infinity algebra, basically. What we did, we saw recently that with this given geometrical data, we can construct something which is called curved L-infinity algebra structure, while Andreas and Christian sort of constructed L-infinity algebra structure, but homotopy relations defining this L-infinity algebra were closing only up to strong constraint. So as I say, it's basically matter of how you package, how you interpret your geometrical data in a different setting. For us, I think our repackaging of this data within the curve and L infinity algebra, we think it's relevant because now we can construct homological vector Q, which will square to 0. And this is important if you want to somehow include this structural symmetry structure in a field theory. We are particularly interested in sigma model. And then also you can discuss the BV-BRS3 formulation of this theory and stuff like this. For all this, you really need bona fide Q, a homological vector that squares to 0. But I will come back to the interpretation later on. So, what is DFT algebroid? I will not tell you how we constructed it in this paper with Thanasis, Faction, and Richard, but I will just give you a definition. So let's say this calligraphic M be a 2D-dimensional manifold. A DFT algebroid is quadruple, consisting of vector bundle L of rank 2D over M, equipped with skew symmetric bracket, non-degenerate symmetric for bilinear, and the smooth bundle map ρ from the bundle L to the tangent of the two-dimensional space-time, such that certain properties of this structural data holds, in particular, and these are given here. So this is basically, the second one is basically the Leibniz rule for the bracket. The third one is compatibility condition between the bilinear and the bracket. And the first one gives you something interesting I will show later, where this D is actually, it's a map from functions to a bundle, but it's actually a differential and it has this particular form for DFT algebroid. So these two properties are sort of looking similar in, for example, current algebroid. You will have this property between this compatibility property between current, between the bracket and the bilinear, and the Leibniz rule.
Excuse me,
Yes.
what is the pairing in the axiom 1? What is the pairing on the right-hand side of two one forms?
Okay, I will show you in 1 minute. Okay.
Okay.
It's basically pairing on the TM. That's the nice part. I will come to this in 1 minute. Yes, thank you.
Okay, thank you.
Okay, so, but before I answer Jan's question, I just want to shortly convince you that what I call here DFT algebroid is really related to double field theory, because, you know, if I give you this definition, it's not maybe obvious how to see it. So starting with the obvious fact is that, yes, you see, I defined my DFT algebroid over two-dimensional manifold. So let's say these manifolds represent the double configuration space of double field theory. Fine. Then what I'm claiming is that the bracket on this on the bundle in the definition of DFT algebroid is actually a C bracket of double field theory. And this you can convince yourself by introducing a local basis of the section of the bundle with following operation. So E is a basis on the bundle, and I introduce the action of the bracket on this basis being proportional to some generalized tree form T, which is actually going to, it's a twist of the bracket. I have the action of the vector on the functions, basically because ρ is the map from the sections to the tangent bundle to the vectors in the TM. So they act on the functions. I have a symmetric pairing on the bundle, and then I have a map from functions to the bundle. And when I introduce this, you can use the Leibniz rule, actually, this property 2 of the definition, to calculate the bracket on the general section of the bundle, and you will get the C bracket I introduced before, plus the twist. As I said, this 3 form here is actually the twist of the C bracket. Okay, and now the young question, what is the pairing? This is the important observation we somehow didn't find very important in our original paper, is that actually the pairing in the bundle, the one I introduced in the definition of DFT algebroid, actually induces ODD metric or pairing in the configuration space. So basically, as the property 1 of the definition says, so this is the pairing of the bundle, and I just calculate what it is in this local basis, and you can see that it actually induces the pairing, the pairing eta AB on the target space. So I introduce ODD, constant ODD metric on the target, and one who read something about parahermitian geometry of double field theory, it's just this parahermitian metric, which is induced by the pairing on the bundle. The importance of this relation here is that this is just rewritten, this one. Actually, it is the source of the strong constraint, which might not be visible now, but when you act on the function, so you see that I have target metric, as I told you in DFT, and contracted derivatives acting on the different function. So this is sort of strong constraint terms, but you will see it later. At this point, what is relevant is that when I compare this expression here with the expression I gave you about the properties of generalized field bind, generalized bind in double field theory, you can see that you can, in principle, identify the anchor map of DFT algebroid with the generalized bind of double field theory. Moreover, if you use the properties 2 and 3 of the definition, so Leibniz rule and compatibility in the DFT algebroid, you can show, and using, of course, the bracket I showed you before, you can see that the fluxes of double field theory and their Bianchi's identities are contained in these properties. So in that way, we make identification between the geometric data of double field theory of DFT algebroid with the content on double field theory. In a sense, we obtain through the pairing, we induce the ODD metric on the configuration space. We identify anchor map of the algebroid to generalized bind on double field theory, and the twist of the bracket actually corresponds to general flux of DFT. So,
may I ask a question?
Yes.
So this bracket that you've got, it's anti-symmetric, but it doesn't satisfy the Jacobi identity, right?
Yes. I always work with anti-symmetric bracket corresponding to Kuran and not to Dorfman in a way.
Right. That was my question. Was can you define a Dorfman bracket for this as well?
Yes. I probably yes. It's just also in L infinity formulation you need, well, graded antisymmetric, but you need defined symmetry. So it's always better to have this antisymmetric bracket for the later purposes, at least.
Okay. Yeah. Sure.
Okay. And just one remark, and this is where I'm cheating a bit. So in DFT, as I told you, in the simplest formulation, your fields are obviously metric, B field, and dilaton. I'm completely ignoring dilaton in this construction. Obviously, in flux formulation or double field theory, you will have additional fluxes coming from the dilaton. Here, there is no dilaton because, well, we never did it, we were lazy. However, you have nice work by Andre Coimbra, Charlie Strickland Constable, and Dan Waldram, and also from Eugenia and Peter, how to basically introduce dilaton in all the game. So I think all you need to do is to go back here and sort of twist the bilinear and the anchor map with e to the dilaton, with exponential to the dilaton, and then proceed with the whole construction, and then you will get the contribution from the dilaton in your theory. But you can always ask Eugenia to explain you this. I never did it myself, to be honest. Okay, so this is sort of relation of our abstract mathematical definition and geometric data of Dft algebroid with double field theory. The next ingredient I need is L-infinity algebra. So let's say that in physics, we sort of rediscovered L-infinity algebra in works of Barton-Zwiebach on the string field theory, where he basically noticed that L-infinity algebra is sort of underlying geometric structure under the string field theory. Mathematicians, in particular Jim Stashev, before simultaneously were also discussing this concept of generalizing Lie algebra. So here I want to give one particular definition, which says that L-infinity algebra is just a graded vector space L with a collection of graded, totally antisymmetric multilinear maps mu I in my notation, which takes I arguments, so elements of this graded space, and give you again an element, one element of the graded space out. In my conventions, the maps, map mu I will have degree 2 minus I, and this map satisfy homotopy Jacobi identity given by this relation. So you have here two nested maps of certain number of elements of your graded spaces. Sigma of the index are just permutation, and these things in front are just bunch of signs, which depends on your grading space where your elements live, in which particular grading they have, and in general, very much about your convention. So be sure when you are working with L-infinity algebra that you are sure about which convention you are using, because this bunch of signs are usually different in different conventions, and then you need to be careful when comparing. In any case, L-infinity algebra is just graded vector space and bunch of the multilinear antisymmetric maps, graded maps, which satisfy this identity. Notice, however, what is important, that here I have a sort of pre-index I, so I have actually an infinite number of identities for each I, which in my case here goes from 0 to infinity in principle. So let's open this whole identity for a couple of first i's. So let's start with I is 0, which you just get that the map mu1, which takes one argument, and in this sense, in this case, the only argument is the map mu0 is equal to 0. This is not very illuminating identity. When you take I equals 1, you will from this homotopy identity, you will get the expression mu1 square of some element in your graded space equals to mu2 of mu0. And this element, in the standard case, when mu sort of in a flat or standard L-infinity, this mu0 is 0, and you get something like mu1 square on L is 0. So basically, you have a differential on your L, on your graded space L. If you take I equals 2, what you get in the absence, notice here, in the absence of mu0, you will get that mu1 is derivation of the super bracket mu2. In general, however, you have additional term coming from non-zero mu0, and then, I equal t gives you generalized Jacobi identity, and so on and so forth. The standard examples are, of course, L-infinity algebra is just generalization of a graded Lie algebra. So if you take all the maps to 0 except map mu2, you will have just graded Lie algebra with mu2 being graded Lie bracket. You don't have differential, and then you will have just the non-trivial expression here will give you just Jacobi for your Lie bracket. Slightly non-trivial example is also quite standard. It's curved differential graded Lie algebra, and this is the first example where you have mu0 map. You have mu0, mu1, and mu2. So curved differential graded Lie algebra consists actually of graded Lie algebra G, derivation D of degree 1, and the curvature element R of degree 2, such that these two conditions holds. So you see D is the derivation is not differential, doesn't square to 0. And in L-infinity terms, you just compare these with the maps I gave you, so you can identify the curvature R, which is constant, let's say, with this mu0 element of L-infinity algebra. Your derivation will be mu1 map on your new L-infinity algebra, and your graded bracket from here will be map 2, and then you will have only first two non-trivial identities. You'll have more, first two non-trivial identities, which will give you exactly your graded, curved differential graded algebra. My favorite example, though, obviously, is current algebroid, because I learned half of this stuff working with current algebroid. So current algebroid is a quadruple, again, of bundle over manifold vector bundle of rank 2D over D-dimensional manifold M, equipped with a skew-symmetric bracket. Again, Mark, I'm working only with the current sort of skew-symmetric bracket, bilinear pairing on the bundle, and bundle map, anchor map from the bundle to tangent space of the manifold. And all these and there is, of course, number of properties which the structure between the bracket, bilinear, and anchor, which have to satisfy, and I will not give it here. It was shown by Reuteberg and Weinstein that you can, given the current algebroid, you can write Lie infinity algebra for it. And this observation is based on the following, is that actually you can sort of extend the current bracket on the whole of this resolution space of H, and then define L-infinity structure on basically on this space. What I forgot to say here, and it became obvious now, of course, L-infinity algebra from this mu element, mu0 element being 0, when you can define differential, mu1 that squares to 0, actually has underlying chain or cochain complex under it. Of course, because I have this differential and then I can define it. So in the case when mu0 is not 0, I don't have chain complex underlying L-infinity algebra. So they basically use this complex to suggest L-infinity algebra for current algebroid. They actually had one more space here, this space of constant, but since it's not involved in any homotopy relation, I'm not writing it. So basically you have two space of function manifold, and you have this vector space of the section of the bundle. And they show that if you define the maps given here, these are all the maps. So mu1 is this map, is this differential that goes from the functions to the section of the bundle. Your mu2 map is current bracket. Your mu2 map between sections and function is just bilinear. So you leap the functions to the bundle and then evaluate it on the bundle bilinear. And this third one is just telling you what happens with your Jacobi identity for the bracket in the current algebroid. And homotopy relations I show you, which are compatibility between this map, gives you exactly back the properties of the current algebroid. So they tell you that map rho is that this differential is the kernel of the map rho, that the map rho is homomorphism, and that Jacobiator is 0 up to the exact terms in I. These are defining properties of current algebroid, where I show you what is Jacobiator and actually Nienhausen function given here. Yes.
If I have a current algebroid, then there's a Chavera class associated to it, like the three form, the closed three form. Is there a way to see that nicely in this picture, or is it just kind of hidden in there somewhere?
Oh, yeah, I have no idea. I never thought about it. So for me, well, here you don't see anything.
Yeah,
it's just,
I mean, it must be
sitting
somewhere
in the bracket.
But I was hoping that there was a nice, okay. Yeah.
Sitting in a bracket. It's basically sitting also in sort of here, because this is the only part which will survive. So
okay, yeah, I was kind of hoping that there was some nice, real simple interpretation, but I guess it's all locked in there somewhere.
Here, yeah, I don't know how to sit here, to be honest. Yeah.
No, thanks. That's okay.
So this is how you get sort of L infinity algebra for current algebroid. What I did with my student is that we sort of, what they did is to say, given current algebroid and current algebroid bracket, I can leave this bracket to the whole sequence, and then I get this L infinity algebra. We sort of wanted to reverse the approach and says, given this L infinity algebra, so we just extended, we included basically the tangent bundle in the map, in the graded space, and added one map. If you do this, and this start from the L infinity given like this, you will get out current algebroid. So in a sense, we sort of made the thing inverse in the construction. We just say, starting from this, I get current algebroid out. Their starting point is different because since they start from the current algebroid, they can completely ignore this H space, which turns out, I mean, this is the vector space. This is the space of tangent vectors here. And this is the map rho, which they don't use in the L infinity. In their L infinity, map rho just magically appear because you have current algebroid, so you know that there is in this differential operator D, there is rho sitting. There is that this D is in the kernel of this map. You don't have it explicitly given in the maps, but you know it somehow there is because you know what is current algebroid. I'm just saying, if you don't know what is current algebroid, I'm telling you it's given this. We just added this map explicitly in the space and in the maps, but it's completely the same. All these maps with this additional one satisfy the same homotopy relation, and you get out again defining the properties of current algebroid. Okay, now that you know everything about double field theory and L infinity algebras, I can tell you, okay, this is L infinity algebra for the DFT algebroid. Note, first of all, I don't have these nice errors here because I have curved L infinity algebra. I don't have a chain complex. So there is a map between these two spaces from space L of degree L minus 1 to the space 0, again from functions to E. It's the same map D, yeah, formally the same. I mean, again, it's the composition of the differential and transposed of the anchor map. So there is a map between these two spaces. I don't have mu1 map here because these two spaces are apart for 2, and my mu1 map just has degree 1, so it would raise only 1 degree. So this starting point looks exactly the same formally as in the current algebroid case, but then I have these additional maps, and exactly these four, no more additional maps, which include this sort of degenerate one-dimensional vector space of constant curvature of L infinity. And these are the maps. And if I tell you this is your L infinity algebra, what you get out of this from homotopy relation, so you know your spaces, so you have functions, you have sections of the bundle, you have some constant curvature mu, and these maps, and from homotopy relation, you get basically defining properties of double field, DFT algebroid. And these are these three properties. If you remember, in the current algebroid, the right-hand side was 0. So the D in the current was in the kernel of rho. Here it isn't. There is abstraction by this induced metric on the target, which I identify actually with my mu0 element. It's a constant metric on the target. Map rho is not homomorphism. There is an abstraction, and this again is a control by this target ODD constant metric, which corresponds to my constant curvature element in L infinity algebra. And Jacobiator is not given only by the exact contribution of Nienhausen function, but it has again a contribution that is controlled by this mu0 element of this mu0 element of my graded L infinity space. So here I gave you a small map. So I have my bundle. There is this pairing at the hat on the bundle that I can think of as a map from L to L. Dual FL. I have rho star, which is transposed of my anchor map, which I have in my DFT algebroid. I have induced map eta between tangent and cotangent bundle over my target space. And very weird thing I have inverse of a map. I have inverse of an anchor. And this is the relation that holds. And I know it sounds bizarre to have inverse map, but I don't have a kernel, first of all, and second of all, if you remember, I identified my anchor with the generalized Filbine of double field theory, and as in most physical application, I'm sort of assuming that Filbine is an invertible thing. So therefore, here, I have this weird thing, which is like inverse of the map, which sort of exists. So as I say, there is this eta is this induced. So map here, which is induced by pairing here. This is constant metric. It has inverse. Obviously, it's a constant map. And this element is the element I am actually identifying with my constant element of the graded space L2. And I could choose any. I will tell you later why I do choose this one to be sort of mu0 as this constant bivector eta inverse. Okay, L infinity morphism we are not discussing. So I have this symmetry. I have L infinity formulation of my DFT algebroid, and what do I want to do with it? Well, we know that L infinity algebra actually as underlying geometric structure of BV-BRST formulation field theory can incorporate full on-shell content of a classical field theory, which was nicely reviewed in these two papers. And up to now, I sort of just described the symmetry part of my wannabe field theory one day. In order to describe fields equation of motion Netter theorem, Netter identities coming from the second Netter theorem, I just need to extend my graded vector space to incorporate spaces which will contain fields, which will contain equation of motion, which will contain Noether theorems, and go on, and define corresponding map. Also, normally what you want, so this can be always done. This is L-infinity structure. You can incorporate classical on-shell field theory. In a sense, you can always incorporate fields, equation of motion, identity, just extending your symmetry structure you have. Think of this as sort of BV, BRST when you do it as a deformation. You start with a sort of free theory with the symmetry, basic symmetry, and then you're calculating BV compatible interactions and extra symmetries you can get. This is the same way here, sort of you extend your theory step by step. Sometimes you also want to have an action because, you know, we like to have equation of motion, but we also like to obtain them from some kind of variational principle from the action. However, this needs additional input. It needs cyclic non-degenerate inner product. Basically, you have to define an integral, and this integral also have to have certain cyclicity properties, and these cyclicity properties have to be compatible with your L-infinity structure. So this cyclic non-degenerate inner product is external extra data you need, and it does not always exist. However, you can always define at the level of the field equations, you can always define L-infinity. If you have extra stuff, you will get also an action. In order, for example, in our setting, to go towards constructing an action for things, because we are interested basically in the sigma model for double field theory, we will add one more space, the space of grading L1, which was missing here, which would be basically my space of vector fields. I would need to extend my maps. So I extend the space. I had to add some additional maps and then try to see how can I use these to construct my field theory. Just to a small note, for the target space action of double field theory, there are some results of Olaf and Barton and also Eric Lescano with Mayo recently. However, they use L-infinity, which is based on current algebroid. They're using it on the strong constraint. So it's their construction is different from what we do here. So in this sense, I have somehow prepared everything to write down sigma model if only I could find the proper inner product. However, even before I do this, what I can tell you is that given a curved L-infinity, any L-infinity algebra, I can always calculate Q vector that squares to 0. I can always find degree 1 Q vector that squares to 0 for any given L-infinity algebra. Basically what you do, you go into dual picture. You have to construct basically codifferential for your graded algebra. And from there, you just sort of read off your Q vector. So this is the Q vector that squares to 0. So squaring to 0 of this vector will just reproduce the same homotopy identities I told you from this homotopy relation of L-infinity algebra. It's a sort of dual picture. And this is what sort of tells you why Andreas and Christian had a different answer. They have non-negatively graded pre-Q manifold. I have allowed negative grading here in order to write the Q vector. So you see, X is the field of degree 0. Think of this coordinate. This is f is of degree 2. I have degree of A is degree 1. However, my mu0 element, when you go into dual picture, will have the grading -1. So in a way, I went outside of what they were considering. I allowed for the negative grading. And if you look the Q vector I give you here and just sort of forget the red terms, the structure is the same, although not the space is not. The structure is the same as in current algebroid. In current algebroid, only you would have 2 degree 1. You would have 2 degree 1 vector fields, and then because you would have 2 degree 1 vector fields, 1, 0, and 1 of degree 2, you would also have non-degenerate, sort of you can see that you have the symplectic form, you have a Poisson bracket, you actually have QP manifold. Here, I'm not sure if I can ever write, if I can find non-degenerate symplectic form. So what I have so far is that I know how to write curved L infinity algebra for the DFT algebroid. This gave me a way to construct homological vector field equal to 0. Now, what I would like to do next is to reconsider the construction of double field theory sigma model and see how can I obtain this from the L infinity algebra, because what we were also interested is also in the sort of PV formulation of this model. I have to say, I'm not sure if I know how to write non-degenerate symplectic form. However, there is very nice work by Grigoriev and Kotov on pre-symplectic AKZ formulation, which they did for the gravity. So I'm hoping we can apply something similar here. The second thing I would really like to discuss at some point, and I'm just keep repeating this from one talk to the other, failing to do the precise calculation, is that basically you can see the strong constraint in double field theory as being just a sort of expression of Hopf anomaly. If you remember, in the beginning I told you, you have in double field theory global symmetry group ODD. However, you cannot gauge whole of this group. If you gauge whole of it, you will get Hopf anomaly. This is just by definition Hopf anomaly. I have a global symmetry, I want to gauge all of it, and then there is a part which breaks the gauging. And then you see you can only gauge part of it, and this is all. So in a way, you have to impose too strong constraint so to kill the Hopf anomaly. I want to see this precise statement actually sort of at the level of the sigma model. And finally, just some hand-waving arguments why we all do this complicated mathematical construction and we are claiming that we pretend to be physicists, is that what we, let's say, ultimately want is to solve quantum field theory. It's a very difficult task, unless you are giving sort of harmonic oscillator kind of example. So physicists have come with different tools that can approach really solving the idea of solving or understanding non-perturbative structure of the field theory, if you want the same. And these tools usually includes integrability properties of a certain field theories. Then we are also keen on dualities, because like in this example, dualities always give you sort of way to probe different regimes of your theory, so you can have certain feeling about what's happening in different regime. Or you can also combine different perturbative expansions, expanding about around standardly we expand about coupling constant, but recently people start thinking about expanding field theory around large conserved charge. This gives you different perturbation theory, and when you combine them together, you get new information. which from the perspective of one or the other are non-perturbative information about this theory. Here, I just want to sort of quote Zwiebach on the meaning of this curvature or curved L-infinity algebra. And in the context of the closed string field theory, Zwiebach actually claims that think of this curvature as you're sort of expanding your theory, not around the solution of equation of motion. You move it by a constant shift, and then you expand there. I mean, you can always do that. It just sounds stupid. I mean, your expansion is way more complicated because you will get terms that usually don't cancel. But from the perspective of the string field theory, this is sort of relevant because you want to think about sort of off-shell formulation of strings, or as he says, a problem, can you discuss string field theory without use of standard conformal background? So for him, moving away of classical, of the solution of classical equations of motion means moving away from conformal backgrounds. And I think from the string field theory point of view, this is interesting. And that's all. Thank you very much.
Thank you. Are there questions? Okay, then maybe I can ask about at some point you said that for the BV-BRST with DFT L-infinity algebra, you cannot still find the symplectic two-form. And maybe I was wondering if it's just, what problems do you have for that exactly? So you cannot read it from the homological vector field?
No,
Like,
so L-infinity plus this cyclic integral you have, it's actually QP manifold. So it has both Q structure, the homological vector field, and Poisson.
okay.
Or non-degenerate symplectic. So far I have been able to find Q. I'm not sure that in this setting, I mean, normally you could have, any Q and some P and you're happy. So, but so far for double field theory, well, to be exact, for sigma model of double field theory, I haven't been able to find one. The reason I suspect it's might be actually degenerate symplectic form. So I would have a symplectic, pre-symplectic form. So two form which is degenerate is the way I can, because the way how I constructed this DFT sort of algebroid is that I started from current, the algebroid defined over double space, and then I did certain projection. Current algebroid is QP. QP2 actually, it was shown by Reutenberg. So I have Q, I have non-degenerate symplectic structure. But when I do the projection, the projecting out things from the symplectic, I mean, I cannot just project symplectic structure. I will have some things that are sort of in a are not observed by this symplectic structure, but they can still appear in a sense. It would be degenerate. Now, this is how I think of it, because this is how I construct it. Maybe there is a way you construct it differently, like sort of independently, not following this projection. And then maybe you can, I don't have sort of, let's say, theorem saying there is no for this problem. I just expect that there is none because of the construction.
Okay.
But as I said, there is this nice work of Maxim Grigoriev and Alexei Kotov, who say that even though your symplectic structure is degenerate, you can still write the action. You just don't have Poisson bracket. You cannot invert it, or you can invert it only on certain submanifolds of your space. But to write down an integral, you don't need to invert anything. You just write it, it's degenerate, and then on certain Lagrangian submanifold, sort of on Dirac structures or something, you would have a standard construction. But they offer a way to do it, sort of AKZ-like, also for this degenerate symplectic structure. One more thing is that I keep saying AKZ construction is the way to construct geometrically certain topological theory. DFT is not topological, so current model is, in this sense, topological field theory. Current sigma model, let's say, is topological field theory. However, DFT is not. I have dynamical fields there. So in this case also, you would expect you would have certain degeneracy in the symplectic structure. So, but yeah, I don't have a proof. I'm just saying this in a talk. I'm not writing this in a paper.
Okay, thank you.
How do Ramon fields fit into this picture? And do they fit in?
Double field theory people know how to do this.
Okay.
I don't. I never even tried. But yes, you can do it, and up to a certain extent. No, not this construction, double field theory. Then, but
I'm just thinking this these L infinity algebras.
I mean, the symmetry.
I meant to extend Courant algebroids, right? And for Courant algebroids, you know how to do them because they're just like spinners. You kind of encode them as ODD spinners and then just tack on some extra stuff. So I'm wondering if there's a similar picture here, or if it's.
I didn't look. Yeah.
Okay.
All the DFT double field theory people would always work on the strong constraint.
Okay, sure. Which is morally just Courant algebroids, right?
Yes.
Yeah. Okay.
But then we lose.
Sure. I mean, the whole point of DFT, I think, is to go beyond that, right?
Yes.
Yeah.
It's just not.
It's hard. Sure. I completely understand. Yeah. Maybe I can ask another question then. At some stage, you mentioned Vinogradov algebroids, but I maybe missed where they popped up.
Well, at this level, it's the same as Courant. So Vinogradovs are just these QP ones that are constructed of T star and then shift by some degree TM. So they can go, this is 2, this star 2.
Yep.
But for any K, you could write for any.
It's just T star K or something. Or K.
Yes.
Yeah. Okay.
Yeah.
Sure.
It's this class of.
Right. And
QP K.
And I'm sure
algebroid.
I'm sure I know the answer to this, but it's probably, I assume that nobody knows the answer for, if you want to look at these higher exceptional algebroids, what the correct L infinity structure there is. Suppose you want to look at, this these exceptional tangent bundles that are kind of like Vinogradov, but the T plus wedge 2 T star plus wedge 5 T star, etc.
Look at some bits of this. It's very difficult because there are more than one generalization you have to do.
Sure.
There are some works of Alex Sarvanitakis who was looking at this. So
yeah, I've seen some of his stuff, but I wasn't sure if there was anything beyond that.
No, he did something, and recently David Austin also had
Okay.
some paper placed last month or two, I think.
Okay.
And I think David is mostly looking in this current algebra. So maybe you know the work of French guy who basically constructed current algebra just looking at the current algebras on Poisson and sigma models, the algebra of the currents. And
I
then
think Thomas Strobel, could it be?
Yeah, before Strobel, exactly, he had sort of Reutenberg construction using the currents. Now I forgot his name. It's very funny because the most cited work is not ever published. It's an archive, I mean, it's not in the journal. Same time as Reutenberg, more or less. But anyway, David is trying to do it with these higher currents for brains, actually, for brains. So for exceptional generalization of this stuff.
Okay. Okay, thank you. That answered my question perfectly.
Okay.
If there are no more questions, then I think we can stop the recording here, and thank you again. So, thank you.
You're welcome. Thank you.